Yes, they are. I know. Lo siento. We could have done pi over 4, but A, there was only so much room, and B, I kind of hoped we didn't need it. All right, correction papers. Are we shaving with correction papers, Bobby? Sit down. Okay. Work. Whoop. Ah, look at this. Do you guys agree? Sine of 0 is 0, and 0 times 4 is 0. Sine of, calm down, pi over 6 is 1/2. 1/2 times 4 is 2. Sine of square root of 3 over 2 times 4 is 2 root 3, and then et cetera, et cetera, et cetera, et cetera. So why am I going to make my graph go out 4 in every single direction? That's the maximum good. Does that make sense? The maximum radius, the maximum out from the pole and any angle. Okay, so how do we graph polar points? We just do. Don't we graph 0, 0 on the pole? Don't we graph pi over 6? Ooh, are we okay at pi over 6s now? And then 5 pi over 6s? And then do you guys see some pi over 3s? I do. And then some more pi over 3s? Okay, so I'm just showing my pi over 6s and pi over 3s because I'm going to need them, yeah? Although this pi over 6 seems awfully thin. That looks more like 15 degrees. Let me go change that real quick. Got him. It's a little bit better. All right, here we go. Boop, boop. At pi over 6, what am I going out? How do I go out 2? What did we learn yesterday? Out 2, I think about drawing the circle, right? And I ask, where does that circle with a radius of 2 intersect? Are we good? Oops, if we could only get it in the line. I'm not used to writing like that. Okay. That's about right. Pi over 3, 2 root 3. How do we know what that is? Well, hold on. Pi over 2 is 4, which is here-ish, right? So what do you guys think about 2 root 3? That's greater than 2, right? Because that's more than 1. So can we make it 3-ish, maybe a little bit more? Is that okay? So we could kind of like make our 3s and be like, it's somewhere around there. I'm not exactly sure. Okay. So far, I've seen 2 kind of done this sort of motion. Do you guys agree? Ish? It's a little bit rough, but maybe it should be more like that. Okay. Then I go where? 5 pi over 6. Oh, no, sorry. 2 pi over 3 is the exact same as whatever that guy was, so I'll just copy. 5 pi over 6 is the exact same as that guy, so I'll just copy. Oops. Except my units are a little different over here. I think I copied so well. My units aren't quite matching up. And then I'm back to 0. All right. Well, that was kind of boring. Now what? 7 pi over 6 says to go where? Oh. Because negative says go the opposite direction. So if this is 7 pi over 6, am I going towards him? And the answer is no, I'm going away. So if I go away from him, where am I actually just going again? I'm going right back here. Can you guys do me a favor? In your polar mode, in your calculator, can you put in, do they call it R1, R2? Is that right? R1, can you guys put 4 sine of theta? And before you graph it, you guys notice how there's this little line right before R. Is it a diagonal line? Is that what it is? And it's talking about how you're graphing it. And remember, we can make it bold, we can make it dotted, we can make it shade above or shade below. Can you guys go find for me the option that has a circle with a little baby tail on it? You have to scroll back before the R1. Use your little arrow keys to go back before. Can you find for me the circle with the little baby tail on it? And then can you graph? Do you see it go around twice? How does that help? How many thetas did we need to get this whole graph? Did we need 0 to 2 pi? No, because it went around twice. we actually only needed half of the normal period. We only needed 0 to pi. Now, is it bad that we went to 2 pi? No, it was fine. But did we need our table to go that far? Because what did it start doing? Repeating. So technically, if we're just trying to get the path, if we're just trying to get what the graph looks like, the graph of the looks like, maybe it's helpful to know the period of said polar equation. Or maybe it's helpful to know, hey, if a polar graph ever starts over, you can stop. So if you graph point by point by point, and if it's 7 pi over 6, you're like, wait, oh, all right, it's going again. And then you could see, oh, it's going again, and it's going again, and it's going again. So that's just kind of like a technique in that as soon as you got to 7 pi over 6, you could have been like, I'm done, forget it. It's just going to repeat. So what was the period for this graph? How long did it take for the path to complete? Just 0 to pi. So that's all I really needed in my table. Now some of you are like, why didn't you do pi over 4 and 3 pi over 4? I could have, but you know how I estimated this one? I would have had to estimate another one. It could have kind of thrown me off if I had done too many estimatings, and I would have been a little bit without going to my calculator and getting decimals and making it more precise. So usually if I'm going to do one with radicals, I usually try to do only one, so I'm estimating, but I'm not getting confused trying to compare like a root 2 with a root 3 and what's the difference. If I was Mrs. Leon and had the radicals memorized, well, it'd be a little easier, but I'm not. I'm me. So what are some techniques with graphing polar equations? The title of section 10.8, consider thetas. Make a table. Consider thetas. Make a table. Old school, a tablet. Old school. In Algebra 1, when you didn't know what a graph looks like, you made a table. We're doing the same thing here, but instead of plugging in x, getting out y's, or parametric, instead of plugging in, who would we plug in parametric? T's, and getting out x's and y's, now we're plugging in thetas. Now we're plugging in. And I'm going to say saying that. Is square root of 3 over 2 a really nice value for me to put on a graph? No. How about square root of 2 over 2? No. But in this last graph that I did, I said as nice as possible. In this last graph, could I have skipped these entirely and just gone from here to here to here? I'm not sure you guys would have known that you were going out. Now maybe you would have. Maybe you would have guessed that. But sometimes it's really hard not to have any of those radical values. But try to keep it as nice as possible. If you're going to use one radical value, maybe don't use the other, which is what you saw. Actually, this is the book's version of a table. They left out the pi over 4 also. They were like, one radical is enough. If you can go completely nice and only do the nice fractions, only choose when sine is a half angles or when cosine is a half angles, well, then that'd be great. But you might have to get a little more used to polar equations first. So for cosines, if your equation is in terms of cosines, I would use pi over 3s for sure. 0 pi's over 2's, yes, yes. But I would use pi over 3's. Why? Because cosine of pi over 3 is a half. It's a nice value. Maybe you have to use a pi over 4 or a pi over 6. Just choose one. But for cosine, for sure, use pi over 3's. And for sine, I'm going to say for sure use, well, when is sine nice? Not there. Pi over 6's. So in general, cosines are nice at pi over 3's. In general, sines are nice at pi over 6's. Now, if it starts being cosine of 2 and 4, then maybe we'll change this up a little bit, because then you start multiplying by that number, and it can change a pi over 6 to a pi over 3, and then, but there you go. But once you graph like a table, once you plug in all these different angle values, there are a couple different ways you can confirm that you have the right graph. One is the easiest one, which I had you guys do by calculator. In our polar mode, we've been kind of working with that one, trying to figure it out. The second one is by memorizing the types of polar graphs. and their, that's a weird and their corresponding equations. Which doesn't sound as much fun as a calculator, right? But it can still be useful, especially on a non-calculator part of a test. Although this is going to be a quiz. It's going to be more of a quiz, a quest. But you could confirm by a calculator using polar mode, making sure that your table was okay, or by memorizing the different types of polar graphs with their polar equations, or their corresponding equations. You do one more, but let me go show you that chart of polar graphs. There are like actual general equations that do tend to go, well, okay, these general equations are going to go to all four of these different types. And depending on what's going on, sometimes depending on how big A and B is, if B is bigger and I can subtract because of cosine being a -1, then it's going to be going, and all of a sudden it's going to be doubling in, but it's not going to be repeating itself, and then it's going to go out and be positive again. It's going to be positive most of the time, negative for a little bit, and then positive the rest of the time. This one's going to be positive until it hits 0, but it never goes negative. That's going to happen when A and B are equal, because sine can go to -1, which would make them cancel. But that would give a little what we call a cusp. This one's called a cardioid because cardiac arrest, cardiac surgeon. What's cardiac? Heart. See the cusp? It's a little baby heart. I mean, it's a very distorted and weird, bulgy heart. Anyway, but that's the cusp right there. Boop, boop, boop. It's called a cardioid. This one is called a dimple limmason because it can't even get to 0, which means A must be bigger. Not tons bigger, but bigger enough that it can never get to 0 when subtracting when sine or cosine is -1. So it just kind of flattens out like maybe the bottom of a hard-boiled egg. But it dimples a little bit, but not a lot, not enough to go in. And then this guy's just flat. But, long story short, you can do that for actually quite a few different typical or special or, what do I want to say? Frequent polar graphs. There are more than those, but those are the basic ones that you will see over and over again. Now, some of you might have memorized that, oh, this is an A plus B cosine of theta. I think it's one of those limmason types. Oh, it's a French word. It might be one of those limmason types. So we're going to go ahead and, how are we doing on time? Okay. We're going to go ahead and graph this guy. Because we just talked about, hey, we can make a table, we can choose thetas, we can graph. We're going to graph this guy, choosing our own thetas. They're not there for you this time. Maybe you're going to go between 0 and pi and hope that it's enough. Maybe you're going to go between 0 and pi and I'm going to keep going because I'm not sure that is enough. And then we're going to talk about some clues as far as tricks to getting these equations, or you already have the equations, sorry. Tricks to getting the graphs. And if there are any shortcuts that we can take. Now I want you to pick your thetas. Collaborate in groups. What thetas are you going to do? You're going to go between 0 and pi? You're going to use every single unit circle? Or you're going to narrow it down and only try a few? Can you figure out what type of graph this is? Can you figure out what type of graph this is? What angles are you guys using? Raise your hands. How many of you guys are going between 0 and pi? How many of you guys are going between 0 and 2 pi? Oh, okay. How many of you guys are using pi over 6s? Pi over 4s? Pi over 3s? Oh, you guys are being bold. The rest of you guys are just doing nothing? Half the class is not even trying? You're not supposed to use a calculator. That's how to check. That's how to check. That's not how to graph. That's how to check. Well, I saw hands on 0 to 2 pi, so I guess I have to model that. All right. And then I saw more hands on pi over 3 than anything else, so I guess we're going to try to be bold and just skip and not do any radicals. You guys didn't do any radicals, huh? All right, that's bold. All right, when we plug in, cosine of 0 is 1. What's 3 plus 2? Do you guys know that before I fill out the rest of this table, I know that's the biggest r I could possibly come up against? How can I know that? Just by thinking about the equation. Kyle? Why? At 0, cosine is 1. And why is Adam saying that's the most? What's he thinking? At 0, cosine is 1, and that's the most. Unit circle, 1 is the max. You guys hearing? Cosine goes between 1 and -1, so 1's the highest, right? If 1's the highest, 3 plus 2, everything else is going to cut 2 down. And that's what Kyle was trying to say with the fraction idea. Yeah? Okay, so I know right away I can go ahead and make this. I'm going to make it smaller, though. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Yeah? Okay. Pi over 3, what's cosine? Why are you guys choosing the pi over 3s? 3, 2, 1. It's 1/2. It's a nice one. Okay, so what's 1/2 times 2? 1. And what's 3 plus 1? Pi over 2, cosine is 0. 3 plus 0 is 2 pi over 3. Cosine is -1/2. -1/2 times 2 is -1. What's 3 minus 1? 2. And at pi, cosine is -1. And what's 3 minus 2? 1. And if I go 4 pi over 3, which puts me in the third quadrant, cosine is once again -1/2, and -1/2 would once again give me 2. I think I see a repeat. Let me go see what happens. So at 0, I'm going to show a 5. At pi over 3, you guys get that I'm doing my pi over 3s because that's what you chose? At pi over 3, 4, I'm going to connect my 4 with a circular sector, and I'm going to put a dot where it intersects. Pi over 2, I get a 3. 2 pi over 3, I get a 2, so I'm going to connect my 2's in a circular sector. There we go. And then all of a sudden, I'm at 1. Huh. And then all of a sudden, once again, but I'm not at a -2. I'm not going back. At 4 pi over 3, I'm at a +2. So it's something new, but, huh. What do you guys think is going to happen? Symmetry. Symmetry. Because haven't I gone through the cosine being all the positive 1 to 0, and then 0 to -1? So what's going to happen again? Cosine's going to go from -1 all the way back to 1. It's doing its cycle, and as it's cycling, well, I'm not going back. I'm not repeating. It's not like the one you just graphed where it just did the same thing twice, but there is going to be symmetry. So guess what? If I was to go to 3 pi over 2, well, pi over 2 was +3, and 3 pi over 2 is going to be +3 also. Pi over 3 was a +4. Guess what? Negative pi over 3, or what? Oh, I didn't even do that one, did I? Oops. It's also going to be 4. And then it's going to come back to the beginning. So even though you could have gone all the way to 2 pi, and even though if I was going all the way to 2 pi, I apologize. I should have included my last pi over 3 angle, which would have been 5 pi over 3. and then 2 pi. What would have happened is symmetry. It would have been 2, which we already found, and then 3, and then 4, and then 5. And so you just had to go out 2, and then 3, and then 4, and then 5. Ha-ha! Who is this? It's a dimpled limaçon. Isn't there like a little something Frenchy accent? Oh, it's the C? I thought it was the O. Gracias. Isn't it like a little upside down hook? Does it go that way or the other way?
It's like a question mark.
Yeah, but like upside down, right? It has a little. Anyway, a limaçon. What's limaçon mean in French? It's like escargot, but not. It's snail, but not the food.
Ooh, I love escargot.
But not the food. But why is it not a cardioid?
It's not dimple.
It doesn't go all the way into the pole.
Oh.
It's like a little baby dimple, a little bit of that, right? It's a little baby. I don't have a dimple, or else I'd show you mine. They're cute, though, people that have dimples. But it has a little bit, but it doesn't have a total cardioid. It's not a total cardioid. Anyway, could we have that memorized? Yeah, we could have that memorized, or could we just get really good at making tables? Guess what the Calc BC kids are doing, or having had to do? Yeah, they actually had to, well, they needed this to do what they had to do in calculus. But no, I gave them a choice too. I said, guys, you can memorize when you get the different graphs. Or you can get really good at tables. Some of them are just choosing tables and like, forget it, I'm just going to make a table and get the graph real fast. Some of them are actually trying to memorize some of the key ones. But I gave them a choice. So no, I didn't make it a required memorization because some of them, to be honest, in my brain, I'd much rather just graph it real fast and get really good at graphing. But that's just me. But do you guys see how basically I could have just graphed 0 to pi, and because I knew at least somewhat it was, oh, it's one of those limaçon guys, I'm not exactly sure which one, but if I get half my graph, I'm like, sweet, copy it. So when you get good at graphing, you start to figure out there are some tricks, and one of them is symmetry. When you graph, you start to figure out there are some tricks, and one of those is symmetry. Now, to some extent, this is something we can memorize, and in pre-cal, we kind of do. But to some extent, ultimately, if you ever have to work with polar, it's more of just an understanding. That will naturally occur when you work with different equations. And if worse comes to worse, if you had an equation when you're like, I wonder what kind of symmetry it has, couldn't you just make a quick table and graph it and see? And see if it has, wait a minute, what are the different types of symmetry? Okay, here are the different types of symmetry. Okay, that's one way. Yeah, it is capitalized. With respect to, technically in math, you can just do WRT with respect to. With respect to WRT. Symmetry with respect to, wait a minute, theta equals pi over 2. Why are they saying that? Oh, because it's polar. And polar is in terms of r and theta. And if there's symmetry, what's on this side is on that side. The old way of saying it was y-axis symmetry, right? But what's the new way of saying it? Well, the y-axis, what is that also the same thing as? The theta equals pi over 2 line. Well, technically we could use that guy, but we usually use the standard angle. The theta equals pi over 2 line. Yeah, what's on this side will be on that side. Hey guys, what trig function? What trig function is the exact same in the first quadrant and the second quadrant? What trig function has the exact same values in the first quadrant and the second quadrant? Sine, because cosine, the signs change, right? Only sine is positive, positive in both quadrants. So if you have a function dependent on sine alone, which means only sines, no cosines, it's always going to have theta equals pi over 2 symmetry. What's on the right is on the left, which is kind of nice. Because if it's a sine, maybe we would have drawn our limaçon this way and been like, haha, sweet. But over here, another type of symmetry is symmetry with respect to the polar axis. Now before, this would have been x-axis symmetry, which would have been impossible with functions. Because functions, like rectangular functions, 1x has to go with 1y. It's not like that in polar because all I need is 1 theta to go with 1r. But not only can we have things that fail the vertical line test in the sense of the graph and what it looks like, but we can also have this polar axis, the old x-axis symmetry. Whenever we have a, oh guys, hold on, which trig function is the same in the first and fourth quadrants? Whenever we have a function or a graph that's dependent on cosine alone, which is what we just saw. Check out the equation that we just did. Didn't it just have a cosine with the theta? Now, it had numbers, I know, and adding and subtracting, but wasn't it just the cosine, no sine, no tangent, no secant? And what kind of symmetry did it have? Wasn't it whatever was on top was on bottom? Ha-ha. And then what's the last one? The old origin symmetry. And yeah, you guys are thinking what's the same in the first and in the third? Tangent.
Graph is weird.
Dependent on tangent. Whatever's in the first is also in the third. So guys, there are different symmetries. There are ways of testing as far as plugging in, kind of like we did in the olden days for even and odd for y-axis and x-axis. But the long story short, we were able to figure out who's going to have what symmetry, blessings upon you, by saying the first and second are the same, the first and fourth are the same, the first and third are the same. So if I plug in an angle in the first and the second and it doesn't result in a difference as far as a pi over 6 and a pi over 6 or a pi over 6 and a negative pi over 6 or a pi over 6 and a 7 pi over 6, I can tell my symmetries without memorizing this big old nasty chart. Kiddos, have we started 10-8? Yes. Have I told you basically you just need to get really good at tables? Yes. After the break, you need to have section 10.7